Thanks, Rosemary. Yes. So I was asked to talk about kind of numerical methods, and I felt like for a sort of general audience, it might be a bit too specific to talk only about numerical methods. So I tried to kind of give a sort of slightly more general overview. It's still quite sort of statistical physicsy. There's not going to be a lot of biology, I'm sorry. But there's going to be some non-equilibrium statistical physics, so hopefully it will be interesting on that basis. And just before starting, lots of people contributed to the various things that I'll show, but I wanted to say particular thanks to Takahiro Nomoto, who really contributed a lot when he was a postdoc, so he's now faculty in Osaka, and Jacob was my student here in Cambridge, who's now left and working on AI types. Okay. Okay, so quick outline. So I'll talk a bit about, so the main thing is going to be to talk about fluctuations of time average quantities, and I'll try and give you a bit of motivation for why that's interesting, but mostly I'll just say what's interesting because they're interesting. Interesting things happen when you study them, so that's why I study them. That's the main answer. And then, as I said, I'll talk a bit about, how to calculate these things in complex systems for which you can't do everything analytically. And one of the methods that we started using was this transition path sampling method, and I'll talk a bit about that and an example. And then I'll talk about the cloning method, which is an alternative method for doing this stuff, which one of the creators is in the audience. And I'll sort of talk about how these things are different and how they are similar and what they're good for. And then depending on time at the end, I'll give a sort of more detailed presentation of an example from active matter large deviations. But the talk is a bit too long probably, so it might go fast at the end. But and if there are questions as we go, just shout and I can clarify. I'm happy to do that. And if we don't get to the end, I personally, I don't mind. Right. So if you were here at the beginning of the meeting, then you'll know from talks by Hugo and other people, for example, that large deviation theory is a branch of probability theory that's all about rare events. So that's what I'm going to talk about, is kind of rare events in physical systems. And in physics, large deviation theory is important because it gives a rigorous basis to how thermodynamics emerges from statistical mechanics. And that's been understood for a long time. You can read about it in Hugo's review or books by Elias and people like this. But that's not what I'm going to talk about. But it's useful as context for large deviation theory. So one of the things that I work on is dynamical rare events. So we have a physical system with some dynamics now, and we're interested in rare events as described by large deviation theory. And examples, I won't talk in much detail about any of these things, but examples from glasses, biomolecules, people study a lot of exclusion processes as nice examples of physical systems with interesting dynamics. Active matter, I'll talk a bit about it again. So those are the kind of physical systems that we're interested in, and we're interested in dynamical rare events. I'll explain what those are in a minute. And as I said 2 minutes ago, I think mostly this is interesting because when you study them, you find surprises that happen in fluctuations all the time. So all the time you have a system, it looks quite innocent, symmetric exclusion process, it looks quite boring, particles are just hopping around fine. And then you say, well, what are the fluctuations like? Oh, well, there's all these complicated phenomena, phase transitions, interesting things out in the tails of the distribution. So there's lots of surprises to be found when one studies these things. And that's why I like to study it. And sometimes they also give you an insight into glasses and biomolecules and active matter. But that's not really what I'm going to talk about. Okay, so what's the setup? So we have some classical statistical mechanical physical system with stochastic dynamics. So think about particles hopping on a lattice, an exclusion process maybe, or think about an atomistic liquid in contact with a random thermostat, a stochastic thermostat. And suppose that we have some observable quantity at time t, which we'll just call for now k of t. So it's just some observable quantity. I can measure it in the system at time t. And then I make its time average. So I integrate it from time 0. No, it's that point. Okay. I integrate it from time 0 up to time t and divide by t, and that gives me the time average. Okay, fine. And one of the things we know is that our system is nice and ergodic and well behaved. Then for large times, the time average should converge to the ensemble average. And if you want to be fancy about it, this happens with probability 1. In fact, it even happens more, it happens almost surely. But you might ask, well, how big does t have to be for this convergence to happen? And of course, in glasses, when relaxation time becomes extremely long, that this time required to convergence has to be extremely long. So there are already subtleties associated with convergence to this limit, which have interesting physics behind to do with the glass transition or slow dynamics.
One question about that. Quantity K, could it be something like that for something as current?
Yeah. So yeah.
Basically integrate the current.
Yeah. So if you have particles, then the current is just the velocity. You could just integrate the velocities, of course, and then you can do it with a time local quantity. But yeah, you can count. Yeah. So any additive thing, as you know very well. Yeah. So what we're interested in for large deviation theory is deviations from ergodicity. So in principle, this random object, this random time average, has a probability distribution. It has a probability density usually, and we say that for large times, the large deviation theory says that this probability distribution has a scaling form, which looks like this, where this phi is called the rate function. So phi is called the rate function, and what do we know about it? Well, we know that if we plug in the average, then we should get 1 for the probability, roughly speaking. So the rate function is 0 if we plug in the average, and the rate function has to be positive everywhere because the probability can't be diverging positive. And that's all we really know a priori. Under nice situations, this would be a unique minimum, a unique 0, and so should be convex and other nice things. But so what does the rate function tell us? Phi, it tells us how likely or unlikely are events when this k-bar behaves in a non-typical way. So k-bar should typically be the average. We want to know, what about rare events where it doesn't behave like the average? Yes. Okay, so that's the setup. And this theory, the maths of this was set up in the 70s by Donskoy and Bareland, and it's been studied by many, many people since then. But just that's the math. Okay, so let's take an example. Because we're going to talk about numerics, it's nice to have it. So let's take a system of diffusing hard particles in one dimension. So these blue things, they're particles. This is time going across, this is space going up. The particles have size 1, and they are doing sort of diffusive dynamics, but they don't like to overlap. They're hard, but they can't overlap at all. So it doesn't really matter whether the dynamics is Langevin or Monte Carlo or what it is. In fact, it's Monte Carlo, it doesn't. And then I've tagged one of these particles. So one of the particles is just red, and the others are blue, but they're all the same. It's just colored red, just for fun, really. And then we define our observable quantity to be the fraction of occupied space within the distance a of the tagged particle. So basically, k is large if the neighbors of the tagged particle are close to it, and it's small if the neighbors are at least the distance a away. And the particle size is going to be 1, and the distance a is going to be 0.1. So they don't have to be very far away before k is 0. And then you just make the time integral of k. And then you say, well, what's the probability distribution of this thing? And I like this example because it's quite simple and it fits on one page, and it's quite a simple setup. But it's already a many-body system. So even though we're measuring a property of one particle, there are many particles in this system, and so in principle, it's quite a high-dimensional problem already. We can't solve this by just trivial method, but we can do numerics with this. So a priori, it might not be a very interesting probability distribution, but one thing you can do is you can look at what happens in the tape. So instead of plotting the probability distribution, which looks like a sort of probability distribution, they always look the same, really. Instead of plotting the probability distribution, I'll just plot some events that happened out in the tape. So this was an event that happened where the clustering was large. So K, I'm calling it the clustering because it's large when there's lots of neighbors around the trace. So the clustering is large in this trajectory, and the clustering is small in this trajectory. And these are typical of the values of K bar. So if I can find a trajectory with large K bar, it usually looks like this. If I can find a trajectory with small K bar, it usually looks like this. And you can see that for the large K bar, what's happened is this tracer has embedded itself in a dense cluster of lots of particles that are all almost on top of each other. And this one has located itself in a big void where there's no particles around. Even though K bar is already 0, if there's no particles within 0.1 of this guy, he still embeds himself in a big void with nobody else around. So this is sort of an example of sort of, for me, this is sort of surprising thing that happens in the tail of the probability distribution. So the configurations change in a qualitative way when you just ask, what happens at small clustering or large clustering. So we consider the distribution of this local quantity. We're only talking about clustering around one particle, but we get these macroscopic scale correlations. And we have theoretical arguments that show that this happens in 1 dimension or 2 dimensions. Okay, in 3 dimensions probably doesn't happen, but it's not complete a 1-dimensional artifact, and there is some generality, which you can read about and talk about it. But the fact is, because you've got this long time averaging, then you kind of get long-range correlations that are mediated by the model. So that's the way. Okay, and then the question is, how did you get these results? Because these are very rare. So the longer is the time, the rarer these are. I wanted to look at how rare these are, but I couldn't find the number. But they're pretty rare. You'd have to simulate a lot of trajectory before you see what that looks like. Okay, so you have some choices for how to do this kind of numerics. One thing you can always do is just sample, just run trajectories and wait until the interesting thing happens. And it's worth remembering that that's an unbiased estimator always. If someone writes papers, I've got an unbiased estimator, I've got an unbiased estimator too, just sample direct. Okay, so just having an unbiased estimate is not very useful. But of course, it's very inefficient. Another thing you can do is this transition path sampling method I'll talk about in a minute. And the way you should think about that is that you take your trajectories of your system and you do Monte Carlo simulation on the trajectories. So instead of thinking about configurations of your system, you think about trajectories, and then you do Monte Carlo sampling, which mathematicians would call MCMC, on the trajectory. And that's always available to you. That's the big idea of Chandler and the guys there, and Christoph, and Peter Bolhaus, and other people from Berkeley in the early 2000s. And it turns out that's easy for equilibrium dynamics, and it's much harder for non-equilibrium systems. Or another thing you can do is this cloning method, which boils down to population dynamics for trajectories, which would be called in the math community sequential Monte Carlo. So you can always choose MCMC or sequential MC. They have their strengths and weaknesses, which we'll talk about. The good thing about the cloning method is that it doesn't need any equilibrium. The bad thing is it's a bit more tricky to analyze the errors, I would say. But it converges, so that's. And then there are many other methods that people use, but I would say these are the dominant methods that have proven themselves as being effective for the moment. And I won't really say anything about these, but you can certainly ask about them. So suppose this is my trajectory from time 0 to time t. So I always have this finite trajectory in mind. This trajectory from time 0 to time. I pick some random time, which I'm calling the shifting time, which I indicate by this dash line. And then what I do is I move the shifting time to time 0. So this data line goes to here. This piece of the trajectory is this piece of the trajectory, and I put it now at the beginning instead of being at the end. And then I've got an integrator to my dynamics. Now I can propagate the dynamics forward from this point onwards, and I get a new trajectory. So here I propagated the natural dynamics of the system, and I've generated for me a new trajectory. So this is a way of going from an old trajectory to a new trajectory in which most of it's the same, and some of it's different. And then this is the proposal of my new trajectory, and then I accept or reject. And basically, I accept or reject according to whether the K bar is what I want it to be or not. So there's different ways, different ensembles you could sample. I'll say more about it later. But this is the basic method of constructing a new trajectory from an old trajectory. And it's sort of statistically unbiased because it uses the regular dynamics of the system to propagate the new. And then, as I said, so this is the proposal, just like in Monte Carlo. This is the proposal. You propose this new trajectory, and then you accept or reject it according to whether it does what you want, whether it's consistent with the distribution. And this is called a shifting move. In the TPS sort of jargon, this is called a shifting move. It's only one of the kinds of moves that you can do, but it's a nice one. And with this move, this transition path sampling obeys what's called detailed balance in trajectory space. And the way you should think about that is, if I just take the regular dynamics, then the property of starting with this one and generating this one is related in a simple way to the property of starting with this one and generating this one. But if you're following carefully, you'll realize that this thing itself is not quite a reversible procedure. The way you make it reversible is you pick this time at random, you keep this piece of the, take this time at random. Yes. You keep this piece of the trajectory, and then you have to propagate this bit backwards in time in order to have the reversal. But that's okay, because it's an equilibrium system, so the backwards dynamics and the forwards dynamics are the same. So for this method to work and do the right thing, you need a reversible dynamics behind. You need to be able to propagate the dynamics back, which you can't do for a non-equilibrium system, but you can do for this nice thing. Okay. So that's the sort of transition path sampling idea. I think it's a nice idea. If you want to do numerics for dynamical rare events of any sort, really, it wasn't invented for large deviations, it was invented for barrier problems, actually. It's a nice method. You can use it to explore the possible trajectories of your system and hunt for rare events. So before going on with the large deviation story, we need a little bit more theoretical material. So this is the slightly more precise way to write this large deviation theory statement. So we're interested in the large deviations of this random object, the time average, k bar t. It's got rate function phi, and we say the probability that k bar t is roughly k is roughly the exponential of minus t times the rate function. Okay, so these roughly, if they have precise meanings, this one means equal on a log scale, and this one means within some small window whose size doesn't really matter very much. Okay, so this is not the most convenient thing to work with numerically. So the rate function is not very nice numerically usually, but under reasonable assumptions, we can get this information from some other function, which is called the scale cumulative generating function, which is given by this formula. So you need to take the average of the exponential of the quantity of interest multiplied by the some conjugate field S. Okay, this is all sort of mathematical stuff, but the way you should think about it is large deviation theory is really in physics, the language of thermodynamics. What we're doing here is we're sort of asking about trajectory with a given value of the quantity of interest, and that's a bit like a microcanonical ensemble in thermodynamics. And everybody hates the microcanonical ensemble in thermodynamics; it's a pain to work with. So here we make a transformation to something which is basically like a canonical ensemble. This is much nicer to work with, much more convenient. And this S parameter which appears is basically playing the role of the inverse temperature in the canonical ones. So, I mean, if you never saw this before, you won't understand it in 1 minute, I'm sorry. But the way you should think about it is we have two equivalent formulations of the problem. We can either work with the rate function or we can work with this SGF, and all information is kind of transferable between the two. So just believe me for that. This one is more convenient numerically, and I'm trying to explain. Okay, and then, so I sort of mentioned sort of microcanonical ensemble here. So the analog of the canonical ensemble in this business is what people like to call this biased ensemble of trajectories. So you take, so now we're talking about trajectories. We're talking about paths the system follows through time. Every path has its own probability, and paths have length t. So that's a sort of parameter of this probability distribution. So this here is the probability of the trajectory under the regular dynamics, and this is the probability of the trajectory in some canonical ensemble, which is not this. That's some unnatural distribution of trajectories in which the ones that we're interested in appear more. So the canonical ensemble is a way of driving towards lower energy. Okay, so this is standard sort of the experts and complicated sort of I would say. But all we need to say is that this is just a sort of reformulation of the problem that's convenient for numerical. And it's convenient for theoretical purposes as well. Okay, so that's one thing. And then there's another thing, which is this business, which is called sometimes a dupe transform, or sometimes control theory, or sometimes, well, more things to do with bias ensemble. So we're trying to sample or understand or study rare trajectories of this physical system. And so these, okay, so in this bias ensemble, these interesting trajectories have become typical. The point about the bias ensemble is it shifts the probability onto the rare trajectories of interest. But of course, these dynamics, these trajectories are very rare under the original model dynamics. We have this model dynamics, we're interested in rare events, they're very rare. So what you can show is that the typical trajectories of the biased ensemble are typical for some other model. So there is some model which naturally realizes the rare event. We don't know what this model is, but we know that it exists, and we have some formulae to characterize it. So what's the right way to think about this? Well, it'll become clear with an example later. So in principle, we can build this auxiliary model for which the rare events of interest become typical. And the way we do this is we add control forces to the system's dynamics. So if you think of my original example, I want to have a trajectory with large clustering around my tag particle. Well, what the control force is going to be, it's just going to want to pull the other particles towards it in order to increase its local clustering. But there's still an interesting question, should that force be weak and long range or strong and short range? What kind of thing should you be doing? That's the thing. Okay, and then this is called the dupe transform in some context, or more related to. So there's this very nice general relationship between the scaled cumulative generating function and these control models, which says that when you perturb your model with the control forces, you have a new trajectory distribution. You can compare that trajectory distribution with that of the original model, and you can compute the relative entropy. And then you take this other thing, which says that you want to have unusual values in k-bar, and then you can get your SCGF, which remember is the generation that you want, by just taking the best possible control. As a canonical ensemble instead of microcanonical, there's also a reformulation as a search over control forces which make the system do what you want. And you can think about the system in those three different ways: either rare trajectories, or bias ensembles, or the space of controlled models which behave somehow differently. And they're all sort of equivalent. And they're all numerical. And if you're interested in all this sort of philosophical work, yes. So there's a parameter, right? So you have these control forces, and if you're interested in and that drives you out into the rarity. So the parameter S. So the S parameter tells you how far you are. Yeah, that's the right question. So here's the picture again. Oh, sorry. Can I say this and I'll answer your question 1 minute? Okay. Otherwise I'll get confused. So if we want to find the optimal control, we would have to solve the whole problem. So if we know the control model, then we would have completely solved the problem, which I haven't done, by the way. So the answer is, short answer to your question is that I actually know. But I have good ideas. So if we could find the optimal control, we solve the whole problem. But what we can do numerically is when we propagate this dynamics, so this is my shifting that began. When I'm propagating the dynamics from this point onwards to this point, when I do that, I don't have to use the regular dynamics of the model. I could use some other control dynamic. And as long as I do that, and I do all my bookkeeping appropriately, then I can propose different trajectories. And in multi-color simulation, if you know about this business, if you're smart about what you propose, then of course you accept more and you reject less, and that makes your multi-color simulation. And in particular, you can show that if you had the optimal dynamics, you would always accept. If you have the optimally controlled dynamics, you always accept the multicolor, and then you just generate trajectories for free. Yeah. Okay. So that's a nice trick which people use in this business. Okay, so here are the results. To answer your question from people. So this is a trajectory where this tracer has not very many friends around it, and this is a trajectory where this tracer has lots of friends. And you might ask, how would I generate this trajectory under some typical dynamics? And you can see that, you know, the inhomogeneous density around the tracer extends over a large distance. So what I believe is probably optimal here is something very long-ranged and fairly weak, but it just does enough work to pull all of them a little bit in towards itself in order to generate this kind of big clump. And this system, I believe, can be, if not solved, then understood very well by some sort of superpropagation theory argument. So this isn't exactly what you do in MFT, but I think that this is some sort of MFT type control, which is a weak long-range attraction between the tracer and analog. And when we simulated it, what we did here was we used a sort of an interaction potential that corresponds to the first Fourier component that fits in the box. You basically have attraction and that's probably low. I think you can show that small f. That's probably. So does that help? So here he kind of pulls on everybody, and here he seems to push on everybody. And you know, he only needs to open up a space 1/10 of its diameter, but he actually opens up a space that's much bigger, because that's in the end much more effective, because once you open up the space, it doesn't close very quick. Does that? Yeah.
So, I mean, just with control. So, I mean, how complicated can your control be? For example, I guess you can have one parameter in your control thing, or you have more than one parameter. Like you chose one Fourier mode, but you chose, for example, two result side.
But the optical control is arbitrarily complicated, and in general,
Exactly.
we don't want to.
So you're going to do some kind of bound for today. So you choose from form, then you best in that form.
That's exactly right. So yes, so in the numerical business, you're free to try whatever you want. You know that your method still works. You can see how efficient it seems to be, and you can just poke around. And there's no requirement of this model that you know anything about, that your control is in any sense. All you're doing is you're just tweaking your proposal to your MC, right? So you just want to do something good.
Yeah. And
it's much better if it's simple, because if it's extremely complicated, it's going to slow down the propagation dynamics, which is a problem anyway. So you might trade better acceptance for slower propagation dynamics. So yeah, so practically speaking, I feel like for numeric, the thing to do is to keep it simple.
Yeah, so
And just get the low hanging fruit, and then let the computer do the work, find the complicated stuff. Of course, the alternative is to like go crazy and eat it to a neural network and learn the optical.
Yeah.
And people are doing that's not because I don't think it's a good idea. So that would be I think the two options are keep it simple or machine learning. Okay, probably. Okay, so that was the sort of idea of TPS. And it sort of maybe also illustrates some of these ideas of control, ensembles, large deviations, so on and so forth. And it's a many-body system. This is like a 25-dimensional SDE, really. So you can't just solve a pocket-like equation. For this, you need a numerical method. So this method works in practice. We're able to sometimes find good control forces that improve efficiency. I'm only really interested in models that can do many-body examples. I think it's easy to invent methods that work when you've got 2 degrees of freedom. But this has been tried in a bunch of cases. So we started working on this a long time ago on sort of models of the glass transition, spin models, and atomistic models. And then we worked a bit on exclusion processes. And then the stuff I've shown you is for diffusing hard particles. And these are all sort of situations where this has been shown to work and gives reliable results. If anybody's interested in any of these things, they can ask. In terms of a sort of critical assessment, what's nice about it, well, I think it's not too simple, but conceptually it's all right. Conceptually, you're dealing with trajectories, you sample them, you look at them, you can see the trajectories, it's all quite transparent physically. Because it's Monte Carlo, you can adapt everything that people know about sampling in physics, like parallel tempering or any fancy stuff that you can do, which is nice. And the error analysis is nice and simple, because for Monte Carlo, everybody should know how to do error analysis. So those are the good points. The non-good points are that it only works for time reversal symmetric models out of the box. You might be able to adjust it, but that would be hard. We're interested in principle in the large time limit for large deviation theory, but we always do our calculations for finite observation time t. And then we have to do some sort of extrapolation, some sort of finite size scaling, finite time scaling. That can be quite awkward. And it can be quite computationally expensive. And but that's kind of like, finite size. Okay, so that's the sort of assessment. Okay, so then the cloning method, I'm going a bit slower than I meant. So this was invented by Christian and Jorge Veliti 2006, I think. And it's a completely different method to solve the same problem. So how does this work? So we want to obtain trajectories with a large value of this time average. Instead of having one trajectory, we run a population of trajectories all in parallel, and these are sometimes called walkers. And then at every time t, or every so often, we kill the walkers that don't do what we want, and we clone the walkers that do what we want. And we don't just do this however we want, you do it in some prescribed way, according to some prescribed rules. You do some bookkeeping, you run the algorithm, and this provides an estimate of the SCGF, and it samples trajectories of the bias concept. So here's an example with 4 walkers for a system with 1 coordinate. So this green guy is a realization of the dynamics. And so this yellow guy and this yellow dotted guy and this green dotted guy. And then at this point here, the green dotted guy got killed and this yellow guy got duplicated such that I end up with 1, 2, 3, 4 walkers. And then at some later time, this one got killed, this one got duplicated, this one got killed, this one got duplicated. And at the end, my trajectories, you can kind of see they're systematically biased towards the top of the page and away from the bottom of the page. And this seems maybe a bit arbitrary, but this, if you're smart, you can work out what to do in order to get an estimate at the end of G. And the good news now is that it's linear scaling to get large time. So we just run time longer and longer, we can get the large time limit essentially for free with linear scaling. The bad news is that you need a large population of these walkers in order to have a reliable estimate, and it's not that easy to work out how big your population is to be. That's the sort of short answer of the trade-off. And it works, it doesn't need any backwards propagation, right? You only propagate forward in time, so it's not equilibrium. Okay. It's related to sequential Monte Carlo, if you know what that is. Doesn't require time reversal symmetry. It's very easy for parallel processing. We did something here where we did many clones in parallel just to see what it was like. And as before, there's no rule that says that your propagation dynamics for your walkers has to be the natural dynamics of the model. So you have the same idea before that you can always modify your propagation dynamics, do some bookkeeping, and in principle that will improve your efficiency. The better, the closer you are to the optimal dynamics, the more efficient your sample. And so these are all good points. This is a good point that's shared with both sides, I would say. The slightly awkward point of this is that at the end of this thing, you look at the end of this picture here, at the end of this thing, you've got 4 trajectories, which are these 4 that end, that reach the time point. So the ones that get killed, they don't reach the end. So that computational effort is in some sense wasted. So all the effort you made to generate these trajectories kind of gets thrown out the window. The trajectories that you end up with are these kind of 4, and you can see that before this point, they're all just on top of each other. I have 4 trajectories that are on top of each other for most of the time, and they diverge a bit at the end. So these trajectories that I end up with, they're not at all independent. That's the reason why the error analysis. But you can go to the method literature and you can read about error analysis for SMC and find some formula for variance. Can't calculate that. Error analysis is understood, but it's not very applicable. Okay. So some examples of this. So asymmetric exclusion processes being studied nicely by this. There are interesting things for chaotic dynamical systems to do with more or less chaotic trajectories being sampled. We did some work on kinetically constrained spin models using this method, including the Takahiro, where we used the control method. So these didn't really use the control method much, but here we tried to be clever with the control forces, and it seemed to help quite a lot. And the control forces give you a lot of physical insight. So the control forces tell you a lot about what's going on in these rare events. By working out what control forces are good, you're learning a lot about the dynamics. Energy transport in, for example, Kipnis, Marchioro, Prasuti model, or in like much more complicated physical systems with David Limmer and Tony Dow. And then I'll talk a bit about active matter in the last 20 minutes. But first I want to show something. So I guess most of you didn't get all the details of what happened. But how should we think about this business now? So this is my sort of picture of like what decisions we have to make when we want to do sampling, and it's adapted from this paper with Takahiro, and which was one of the papers where we kind of said, oh, it's a good idea to put control forces and cloning or TPS together. So the idea of putting those 2 things together. So the simplest thing you can always do is just run trajectories and wait for the road to end. So we put that at the origin, that's the kind of baseline method. And then you can do transition path sampling, and that's much more efficient. And then you can do cloning, which is probably more efficient again, but a bit more tricky to deal with. So those are options for more efficient sampling. Or another thing you can do is just keep sampling directly, but use a control method. And that's a sort of equivalent to some sort of important. So you don't sample using the dynamics, sort of regular dynamics, you sample using some steered dynamics that takes you towards the event of interest, and then you have to do some clever important sampling tricks in order to get back to the distribution. So that's always there. But when you see this picture, then of course you realize that what you really should be doing is you should be in this phase where you use a bit of the control forces and a bit of the efficient sampling in order to get. And this, I would say, is where I don't see any reason not to work in this phase. I don't see any reason to work here, and I don't see any reason. So that's what I would encourage people to do if they're thinking about setting out on this dimensional numerical characteristics of line deviation. Why don't I figure it out? And there's a bunch of work. So I made this slide for a workshop in Berkeley about a few years ago now, and not all these guys are here, but many of these guys were there, and everybody, all these people are working on slightly different methods for doing all this kind of thing. There's been more methods since then. So there's quite a lot of interest in this area, but broadly speaking, I think this picture is reasonably valid, but there's a sort of space of methods that have their strengths and weaknesses, and you should choose the right one according to the problem. Okay. Before I go on to the kind of active matter stuff, are there any questions about all of that?
When this half-year simulation showed this trajectory where K is small and then trajectory where K is large, where the particles are directly. So then how do you characterize these half-year crystallization?
So we are far from crystallization, I think. So in 2D, the main thing that happens is when you want more clustering, you kind of pull everybody in, and you end up with this kind of fairly diffuse.
Yeah, but then can you find the relaxation?
We never thought about that. I mean, I wouldn't, if I wanted to find a crystallization temperature, I wouldn't suggest this as a method. But there's an interesting question as to how the interplay of the crystallization transition and the clustering transition would go. There would be an interesting sort of phase diagram there. Phase identity. Yeah. I don't remember what exactly we did. I think for 2D we might have done. I'm sure that this is true for 2D with particles, but we might have done WCA particles in 2D. I don't remember. And I guess they crystallized it as well. So yeah, I'm not quite sure. Yeah, I mean, I guess this example I showed is a bit empty physically, right? I mean, I think it's nice because it shows that very slightly unexpected things can happen even in very simple. And there are plenty of examples where it's slightly more complicated models, even more unexpected. Like that's not really a phase transition. That one I think. Any other quick ones?
Is there no overall trade-off between kind of better control forces and more efficient sampling? And you kind of drew a big block. This kind of correlation.
I think the trade-off is more like how valuable is your time and how cheap is your compute. Right? So you can always improve your methodology, but in the end, maybe it's better just to let the computer grind and do something else. So I don't think there's any. I mean, it's pretty hard to go up here. Well, maybe not. Maybe it's not if you're good machine learning. Maybe it's not actually that. I mean, there are kind of blocks here. I mean, you can get tweaks here, but the points along this axis are a bit more discrete. Probably I'm not aware of anything. But certainly, there's a lot of freedom this way. But it's more about your ingenuity. Okay, let me talk about active matter and then do the rest. So, so I think there's been plenty of active matter in this meeting, probably. So I'm going to talk about active Brownian particles. I'm going to talk about large deviations as a sort of example of, first of all, that we can really do this numerical stuff for quite complicated systems, and second of all, that I think the result is a bit surprising. So we have our ADPs, our active Brownian particles. Each particle has diameter sigma. It moves with some sort of knowledge about dynamics. And the main thing about it is that it likes to swim with velocity v0 in direction e, which is this arrow that each particle carries, and the arrows rotate diffusively with diffusion constant. So this actually is a conservative force which keeps you in interaction with all the other particles, which is what's repulsive. And it swims along its unit vector, and if it's unobstructed, then it's velocity. And there's a Brownian diffusion here, which is maybe. So sometimes when people write this model, they don't have this. Okay, so what are the parameters for this thing? So there's obviously the packing fraction. There's some sort of measure of how much they like to swim, and the measure that we think about usually is the persistence length. So this is how far we swim before we forget our orientation. That's the persistence length, which is normalized with respect to the diameter. Okay. So that's the dimension parameter from there. Okay, there's something to do with the Brownian diffusion versus the rotational diffusion, which we just fix. This parameter is just fixed at 1/3, which is what you get if you just do the sort of thing and just split note at boundary conditions. This is somehow not very interesting parameter. We just fix it. And then there's some energy scale for the repulsive interaction, which we just take to be basically 1. But it's a hard energy. Okay, and I'm not going to talk about all the physics of ABPs. So what happens with ABP is they do motility space separation. It's all very interesting, quite well understood. What happens at the interfaces might not be so well understood. All that good stuff. Not going to talk about it. So I'm going to talk about the Intraumatic entropy reduction rate. So these active matter systems, they're not time reversal symmetric because the particles are swimming. They have a non-equilibrium steady state, which has all these interesting properties. And an interesting quantity in these non-equilibrium steady states is what's called, by us at least, the Intraumatic entropy reduction rate. So I'll say in a minute why we like to call the Intraumatic. This name comes from, I think, mostly from my thing. So for any trajectory up to time t, we can calculate the probability of that path or trajectory. And we can also calculate the probability that the time reversal of that trajectory appeared as a trajectory of our dynamic. So if you think about fish, you have to think that in the forward trajectory, the fish are swimming along, and in the backward trajectory, the fish are swimming backwards along. And of course, it's very unlikely that you see a whole bunch of fish all swimming backwards in synchrony together. But in principle, it has finite probability, at least in this model. And so that's this ratio is very large. And that has something to do with the fact that the system is a non-equilibrium state. With an equilibrium steady state, you have to swim back. Okay, modular comments about parity and time. So the average of this rate measures the extent to which the steady state violates time reversal symmetry, right? Because if these things were equal, then the average is. Okay, never just ignore this. It's wrong. But there are some subtleties in this formula to do with, first of all, what are you calling a path? And second of all, what are you calling time reversal? So what are you calling a path? Well, for example, what degrees of freedom are you tracking? If I've got fish, are you tracking just the center of the fish, or are you tracking the orientation of the fish? What about the little part eating in the middle of the fish? I don't know. The brain of the fish. So the first question is what degrees of freedom go into the path? And the second question is, when you make the time reversal, do you just literally reverse the movie, or do you do something else as well? For example, do you reverse the momentum, which you should do in the second time? So there are some subtleties in here. And if you want this thing to coincide with the physical entropy reduction, which is the heat dissipated in the bath, you have to make the right choice. And the sort of point about the Intraumatic entropy reduction rate is we say, well, I don't care if this has anything to do with the heat dissipation in the bath. I can still define this quantity and talk about it, whatever choice I make for the bath, or whatever choice I make. This is a way of avoiding the question of, is this thing really heat dissipated? We'll just call it Intraumatic entropy reduction rate, and we'll define it like this for some appropriate choice of path and time reversal path. So for this ABPs, a suitable measure of entropy reduction or Intraumatic entropy reduction is the total work done by the active forces. So we take the active force, multiply by the velocity, integrate with respect to time, and that gives us the work done by the active forces. And then we have to make a rescaling, so we have to divide by time average, and we have to divide by the temperature to get it to be an entropy reduction. And then if you just plug in the various things, you take the orientation, you dot it with the velocity, you take stratometric product, and you integrate, and that gives you the entropy product. And then this thing, this thing has the shape of the K of T that I showed before, so now we can do light deviations of this stuff. And what do we know about this? So this thing is large if the particles are swimming around freely, and it's small if the particles are not moving for some reason. So if R dot is very small, or if R dot is not in the direction of E, then this thing will be small. It will be large if they swim. And it'll be negative if they swim backwards. And just in terms of the previous formula, the way this is interpreted is that we keep all degrees of freedom when we define a path, And we don't reverse any degrees of freedom when we define the type. And then that gives you this. Okay. So this thing is of the shape that I showed you before. It's a time average quantity. So it should have a large deviation principle, which says that this probability distribution has a scaling form with a rate function, which I'm now calling I. And because it's an Intraumatic entropy reduction rate, there is fluctuation theorem, which goes back to many famous people in the 90s, that says that this rate function I has a symmetry. And this just comes from the fact that because it's defined as a product of forward over backward, if you make a time reversal, W will change its sign, something will happen to that ratio. Then you can write a fluctuation theorem. You have to be a genius to realize this, but if somebody else has already realized it, you don't have to be a genius. So what does that tell us about these? If you plot the rate function, how does it look? Here's W, here's the rate function. One thing we know, this is the mean here. The one thing we know is that the mean value of the rate function has to be 0. And then if we look at this symmetry, it tells us something about the value of the rate function at minus the mean, which is that it has to be up here. It has to be equal to the mean value itself. So this line has gradient 1/2. And then if we try and fill in this graph now for the rate function according to this symmetry, you would typically draw something like this. So that's the generic shape you expect for a rate function of the entropy reduction in any physical system. So the interesting thing about active Brownian particles is it doesn't look like that. It looks kind of like this, at least for large systems. So it has basically a completely flat piece here, has a funny kink at the origin, it has a funny kink here, another kink there because it's made by symmetry. I'll show you some evidence for this in a minute, but this is what I'm saying. It doesn't look like the generic typical shape that you would expect. It has this other shape instead. And to get this, we have to take a large system and we have to make everything intensive. So we normalize the work by the number of particles, and we normalize. Sorry, this is wrong. There should be 1 over n in front of this I. So you have to normalize the rate function by the number of particles. There should be 1 over n. So if I look at this graph as compared to what I said was the typical generic shape, there are 2 things you notice. First of all, there are some singularities, there are some kinks, and they are phase transition. And second of all, the probability that no work happens at all is much less small. So large rate function means small probability. So the probability of no work at all is not as unlikely as you would have thought. But the system has a mechanism to not dissipate very much. This happens that way. And the reason for this funny shape and kink and everything is that there's some collective behavior that's happening in large deviations. And I'm just going to show you what it is, and then I'm going to stop. So this is an illustrative result for this normalized rate function. We use the Killing method with a very simple control, which just says and you can see 2 things. So this is the mean here. So the rate function is 0 on the mean as it has to be, and it has this sort of thing. But you can see on this side, there's basically no dependence on system size or weak dependence on system size. On this side, there's a very strong dependence on system size. This n is the number of particles. And you can see these numbers are quite small because, well, these methods don't scale very well to large systems. So remember that there's 2 position coordinates and 1 orientation coordinate for each particle. This is like a 100-dimensional SDE or something, so it's not trivial to solve this one. But for 64 particles, you can definitely still see there's a clear trend that the rate function has a strong system size dependence. And we have good theoretical arguments which say that this thing has to go to 0 as n has to infinity and the numerics. And so what's going on? So if you look at trajectories for this side and this side, how do they look? So on this side, you get dynamical arrest. So the system, instead of being a nice sort of fluid of active particles, it forms this dense crystalline cluster that's dynamically arrested. You can see the particles on the outside have their arrows pointing in, which tends to stabilize this dense state. And then on this side, where you actually don't see any kink on this side, but on this side, there's a subtle kink that happens somewhere right here. It's got the long bacon. And what happens is the particles all orient themselves in the same direction. There's spontaneous symmetry breaking despite the absence of any aligning interaction with dynamics, and they all swim in the same direction. Okay, so let's show the movies for that. So this is what the typical behavior looks like. It's actually very close to motility space separations. It's not completely homogeneous, but basically everything's quite spread out. And then this is the trajectory with high active work. So remember I said high active work, high entry production rate means everybody's swimming around a lot. So these guys are swimming around a lot. And these guys are not swimming around very much. And this has got an active work of almost zero. So this is the mechanism, which I said, that allows the system to have a very low active work. Sorry. Thought these were going to loop, but they didn't, never mind. So this is the mechanism, the physical mechanism for very low active work. This is the physical mechanism for very high active work. Why are these mechanisms good? If you think about the control forces, you think about this picture for a while, you can convince yourself that you only actually have to apply control forces to these guys on the boundary and these other guys. And you think of them as sort of like the shepherds, and then these guys in the middle, they're just the sheep. They're just confined by the shepherd on the outside, are just pushing them into the middle. And so there's a very sort of nice control theoretic interpretation of this arrested state, which is that if you want to make everybody stop, just corral them all into a sort of kettle or on the other hand, if you want everyone to move around a lot, what you should do is tell them all to go in the same direction. And then for this system, they never collide because of one some of the AUPs, they don't collide, they're all traveling at the same velocity, dispersion in velocity. So it turns out that everybody being aligned is a very good way to suppress collisions and therefore swim a lot and therefore dissipate a lot. So the amount of dissipation or entry production is just related to how much you mentioned. So this is the sort of punchline, if you want, which I think is supposed to illustrate what I said at the beginning, which is that when we started on this business, I can tell you for sure, we didn't anticipate this at all, and we sort of anticipated this, but only because we'd already understood it in the simple one. And so this is kind of just trying to back up my claim that interesting, well, I think it's interesting, but certainly surprising things happen when you consider these large fluctuations in these, moderately complicated but still quite well understood systems. And that's why we spend our time, some of our time, searching out into the tails of these probability distributions. Okay, so just I see. So ADP summary. We've understood what are the mechanisms for large deviations of entry production rates in these ADPs. For large dissipation, they also go in the same direction. For small dissipation, they form a less arrested cluster. I already said something about this really, so you can think about this for control. We have slightly better arguments than the ones I just gave you for why this is optimal. And then the overall summary. So okay, there's rich behavior in large deviations and average quantities. We have numerical methods, they work for moderately complicated systems. We can't do extremely large at the moment, although it's getting better now. That was already 7 years ago, 3 or 4 years ago when I showed you. These things are not out of the box yet, so you can't just download it from the web and expect it to work for your system. I think you need a bit of knowledge and maybe not experience, but thought in order to get these things working, because it's quite a complicated problem in the end. I think this linked up to control theory is helpful for 2 reasons. First of all, it gives you a bit of critical insight and motivation for what you're doing, and it also helps with it. And I didn't say anything about variational methods or purely control-based methods or tensor network methods or any of that stuff. If somebody wants to know, they can ask me about it. Sometime later. Okay, thanks for listening, and I can take this.
Thank you very much for the lecture. Are there any questions, comments?
The idea is the examples of what is the trajectory which corresponds to take the field.
So one thing you know from the fluctuation theorem is that they look the same as the forward ones, but backwards.
And that's seen by the point.
Yeah. That's why we didn't show the graphs for the negative side, because it's given not just the rate function, but also the trajectories are given by symmetry from the positive part. You only have to study the positive part. So you have to imagine that those guys with the arrow, they're all really literally going back. And this is, this thing has extremely low probability. It's clear. But it's principle. But I'm not showing that. All right. But if you look at it this way, then it does, right? So this is my schematic of the rate function. And up here, it's very hard. Up here, it's very I only showed this part, but the negative stuff, and it's really steep.
For the case of this machine function on this hardcore, you said that in principle you are not entirely sure what are the outputs, I mean, their range. Would you use the acceptance rate in the weak proof or this proof? I mean, high acceptance rate or lower force proposed, are they measurable? The actual optimal controls?
So unfortunately, it's not quite as simple as that, because we might have a good acceptance rate, but still sample badly. If you make moves along easy directions and you don't go along the hard directions, you'll get a good acceptance rate, but you won't actually make any progress for sampling. So you need some sort of autocorrelation function in your sampling, which we didn't measure. That's the kind of acid test, really. Well, you can just use some variational. There are variational methods to get the quality, which is probably better. That's what these like Hugo and Grant like. There is a formula which tells you how good your control is, which you can evaluate, and then you can try and do steepest descent on that by more stochastic gradients, which is what they do.
Absolutely.
No, you never list from the absolute, but you know whether things are getting better or worse. But I think for that problem, okay, the more I think about it, the more I think by MFT we can push down in the right regime, which is probably quite good.
Curious, what covers your choice of this information entropy production rate? What you define as top, or the time of risk top? Is it kind of keeping the degrees of freedom that you care about in some sense, or is it what it's needed to calculate?
It's a good question. Yeah. So I mean, I guess. So there's a few things that you know, right? So if you have a Hamiltonian system, you really do know that you have to fit them, right? And I think that insight got people thinking, well, should I be flipping my orientations or not? When they were thinking about it, and their stuff. And then there's an interesting question, which is that if you just ignore the orientation, can you prove something about the trajectory of the particle? And that was with paper of Etienne and that, and that's quite interesting. To measure time reversal symmetry breaking only on coordinates without mirror. There's no nice simple formula. I think I'm just going to say what I usually say, which is that I mean, the answer depends on the question, right? So how what you choose depends on what you want. And when we did this, I guess when we did the ABPs, we were thinking, okay, what do we have to do to see something interesting? Which I think is a reasonable way to choose what problem to work on. And I think if we made a different choice for the production rate, with a different choice, we would have seen also something interesting, but it happened to be convenient. You know, if you want to do the foundations of stochastic thermodynamics and cycle or whatever, then they say, well, you have to make the right choice and you're constrained by physics. So I think it depends on context.
I'm just following on that. I mean, there was a step you needed for this fluctuation here. Because you make a choice of the thing that you're going to go, whatever the thing you want to track, and then you need the fluctuation theorem for that thing.
Well, you don't really need it, but it's nice if you have it. I mean,
Yeah, because in this sense, because otherwise we would have to do the.
Oh yeah, well, that's true. Yeah.
You'd have to do the minus governing case, and you didn't. So I mean, generally, so what's the how much is that? I mean, how is the choice? Does your choice was that symmetry reflected in the thing that you choose? The fact that you have this theory.
I mean, yeah, not sure. Because I think when you look at the formula in this, when you look at this formula, then the fluctuation theorem I was thinking about this the other day, and I think it's true that the fluctuation theorem should follow from this formula independent of the choices that we make, right? Because it's really just a sort of a statement about time reversal, time reversal forward path. So if you can write your observable in this form for some definition of time reversal path, then I think you should have the fluctuation theorem always. And so that's the constraint, really. Is there a sensible time reversal operation from which it isn't?
Yeah. But I guess, but it seems to me that getting that time reverse path is not, I mean, it's not, seems subtle for some.
Yeah. Maybe there's something that's not rated. I mean, maybe you just run the route backwards and hope for the best. And
Yeah, but I guess that once you have, let's say, a position on one like variable, and it's obvious that it's, then of course, then you know how you do it. But if you're not sure which is the position, which is one like variable, then.
But if you don't want to choose, then you should really ask about the heat dissipate. Because the real entropy reduction rate is the dissipate. So that one's always privileged. And that one's well defined in an experiment, even if it's not well defined in a model. So the real problem here is that if you don't write an equation with heat, then it's not defined by the equations of motion of the particle. So that's why people got into trouble, I think. The models were not complete because they didn't describe the heat.
They have partial models.
Yeah. They haven't modeled the heat flow, so then different choices give you different entropy reduction rates, and then there was sort of discussion. Yeah, maybe it's too philosophical.
Yeah. I want to show you something. I'll show you something.
Okay, good.
Further question, comment?
There's some classification of similarities that we can have in the equation. Some universality.
So when we started, I think we thought that this is really like thermodynamics in d+1 dimension. And then what you expect is that essentially you've got the classification of normal phase transitions in d+1, maybe with some reduced symmetries because of time symmetry. So that's the sort of first one to answer. But I think now we understand it's a bit worse than that, because if you have hydrodynamic variables, that's not something that goes well in the thermodynamic. If you have hydrodynamic variables like you have here, like a density, then I think going back and saying, oh, it's just like thermodynamics in d+1 is a bit wrong. I think it's more like in the field then, one has to do other kind of things. So I would say there's a partial classification. Some cases we understand, some cases maybe not so clear. That's my thought.
Other questions, comments? Some point you mentioned MFT, right? Can we apply MFT ideas or calculations to study what deviation of behavior of your model?
So I think it depends a bit how you think about maximum fluctuation theory. So if you think about this active matter system,
right,
then I believe that the hydrodynamic variables are described by MFT to some level. And so at least the densities, but actually the polarization is far. So this thing is so what am I trying to say? I can't do any real MFT calculations like theta ansatz, all this like exact calculations, but I think MFT gives the right ideas to understand, for example, why is this flat?
Yeah.
I think MFT says, oh, it's because there's a 1/n scaling somewhere. So I think MFT gives you qualitative insight for this stuff, but not quantitative. For the particles model I showed at the beginning with the likely particles, there I think MFT probably does apply.
But this is more interesting.
Yeah. So there are some words in the paper about it, but not so clear. But
You can write down something like MFT.
something like that, yeah.
Any other question, comments? If not, let's start the speaker again.